Hey, so it's Victoria Blackwell, and this is my pre-Caltech project, in case you didn't know. Before I start my actual presentation, I just want to tell you a few things. First, I want you to know that every blue line represents the parent function, while every green line is going to be the transform line. Also, the graph's function, the y equals blah blah blah, can be located at the top left corner. And thirdly, the domain and range can be found at the bottom right corner. I'll tell you this info for every graph, but just in case my voice is like muffled, disordered, or incoherent in any way, you can pause the clip and go back to the graph to see. Alright, so first up is reflections, which is a transformation that flips a figure across a line. In these graphs, I'm going to use the square root function. Simply enough, its parent is the square root of x. In this graph, the domain and range is from 0 to infinity. Since the x-axis and y-axis are the ideal lines of reflection, I'll talk about those. When the y-axis is the line of reflection, the line will be a vertical replica of its prior image. If you want to make a function a y-axis reflection, just put the negative sign inside the function, in this case inside the square root. In this line of reflection, the domain will become 0 to infinity, but the range will stay the same.
Kid, if there's anything you need, just ask your Auntie Deb. That's me.
Flo and Deb. Or is it Deb and Flo? Anyway, Deb looks in the glass and sees Flo, her sister. If I were to draw a line in between the two fish, they'd be an exact replica of each other. And voila, your y-axis reflection. Now for the x-axis. Here, the resulting line will be a horizontal replica of its above image. For a function to have an x-axis reflection, the negative sign must be outside the function. In an x-axis reflection, the range changes into 0 to negative infinity, but the domain stays the same. My image for this is some Sydney sail ships, try saying that 3 times, as seen when Dory and Marlin almost get run over by one when they arrive at Sydney. See how the ship is reflected in the still water? Looks exactly like the actual thing, except upside down. That's how the x-axis reflected graphs look. And now we have translations, aka shifts. A translation is when an image is slid horizontally or vertically across a surface. I'll be using the cubic root function for these graphs. The parent is cubic root of x. Its domain and range is all real numbers, or to put it in another way, negative infinity to positive infinity. When domain and range are all real numbers, they will always be all real numbers unless restricted or reflected. This applies to all of the following graphs. In a horizontal shift, the graph is slid left or right of the image. To make a function have a horizontal shift, add or subtract whatever number you want inside the function. The mime birds are a perfect example for this because they all look alike. It's almost like one bird just slid to the left, then slid to the left again. Vertical shifts. When a graph is slid up or down of its original image. To make a function have a vertical shift, add or subtract the desired number outside the function. These two bubbles are a vertical shift of each other, one slid right above the other. Now time for stretches. For these, I'll be using the quadratic function, whose parent is x squared, and its domain is all real numbers. First up is a horizontal stretch. Basically, this is when a graph becomes longer. To make a graph have a horizontal stretch, multiply x by a number less than 1.
Maybe he only speaks whale.
We need Dory. To find his son. What are you doing? Are you sure you speak whale?
Who doesn't love Dory's whale interpretation? And on a mathematical note, whales are a superb example for horizontal stretches. The little baby whale may start out, just a couple 100 feet long, but then stretch out to be the same length as its mama, almost a mile. Swimming along to vertical stretches. This is when a graph gets taller. To make a graph have a vertical stretch, multiply the function by a number greater than 1. Alright, so we have little Sheldon and Bob, the seahorses in Finding Nemo. The baby seahorse may be short now, but it'll grow up to be as tall as its dad. The fourth transformation is shrinks. To demonstrate, I'll use the absolute value function. Its parent function is the absolute value of x. Its domain is all real numbers. So first we have horizontal shrinks. In a horizontal shrink, the graph becomes shorter in length. Want to make a function have a horizontal shrink? Just multiply x by a number greater than 1. Gotta love them EAC turtles. From head to toe, these turtles average about 5 feet in length when they are outside their shells. When a turtle squeezes itself inside its shell, its length becomes smaller. Hence, the turtle performs a horizontal shrink. Next is vertical shrinks, when a graph becomes shorter. To make a function have a vertical shrink, multiply the function by a number less than 1. Let me give you a short biology lesson before I continue. Sea anemone is a unique underwater flower that shrinks itself when it senses danger. In other words, if a large fish were to pass by this plant, it would fold its petals inside the stem and make itself look like a rock. By doing this, the flower changes from being 6 inch tall to 1 inch tall. Because the plant goes from tall to short, it performs a vertical shrink. Moving on to the more complex stuff, combinations. In the first graph, I'm using the cubic root function, whose parent function is x cubed. It has a domain and range of all real numbers. The first transformation I did was an y-axis reflection, which changed from x cubed to negative x cubed, then a vertical shift, which is the -4. Then I did a horizontal shrink, which is the 5. Here's the final product. Okay, so here we have 2 blue tangfish, which is the type of fish Dory is in Finding Nemo. One has been flipped across this imaginary y-axis. It's been shifted down, I guess, about 4 inches or so, and it's also been shrunk by a factor of 5. So that relates directly to my function. In the second graph, I'm using the exponential function, whose parent is a to the power of x, and the domain is all real numbers. Okay, so first we have a x-axis reflection, so the function becomes a negative. Then there is a horizontal shift, which is the -4, then a vertical shrink, which is the divided by 5. Here's the final product.
I shall call him Squishy, and he shall be mine, and he shall be my Squishy. Come here, Squishy. Come here, little Squishy. Ow!
Jellyfish number 1 has been flipped upside down. There's the reflection. Moved to the right. There's the shift. And then became smaller in height. There's the vertical shrink. In the third graph, I'm using the logarithmic function, whose parent is log x. The domain is 0 to infinity, and the range is all real numbers. The first transformation I did was the x-axis reflection, making the x negative. Then a vertical shift, which is the +4, and then a horizontal stretch, which is the divided by 2. Nemo is like a little marlin, so marlin is like the horizontal stretch of Nemo. He is also slightly above Nemo, making him a vertical shift of Nemo. And he is also reflected across the imaginary vertical line, making him the y-axis reflection. Okay, well, I hope you enjoyed my presentation and understood everything I said or showed you. If there's any questions, you know where to find me. Thank you.